This is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State, and welcome to Module 2 of ME411, or BE411, Industrial Cooling, which is a topic of our Industrial Energy Efficiency course. In this module, we're going to talk about the thermodynamics of the vapor compression cycle. In the last module, we did an introduction about refrigeration and process cooling in general. In this case, we're going to delve into the vapor compression cycle, which is the core of most industrial cooling. You'll recall in the introductory module we talked about units, introduced the concept of a ton of refrigeration capacity. That is refers to a unit that can move 12,000 BTUs per hour of heat away from the space we're trying to cool. And if we're talking about cooling towers, or the place where the heat's being dissipated, a ton of capacity actually refers to 15,000 BTUs per hour. I think as we move through the course, that discrepancy will become obvious, but something you might want to puzzle on a little bit as we move forward. So in the process of what we call mechanical cooling, the core of this is the thermodynamic cycle called the vapor compression cycle. It's based on two really important phenomena of matter. One is that the phase transition of a substance, for example, the boiling point, is dependent on the pressure. We know that water boils at a lower temperature at a higher altitude because the atmospheric pressure is lower. In fact, here in Boise, we're at right around 3,000 feet. Boiling point is right around 97, 98 degrees centigrade. So it's a measurable difference. And the other thermodynamic phenomenon is that during that phase transition, evaporation, condensing, freezing, melting, for example, substances can absorb or release significant amounts of heat, of energy, without changing temperature. And that's what we call the latent heat effect. Okay, so let's go back to the temperature entropy diagram from our thermodynamics class. And typically we start with this kind of dome-shaped line on here, and that's the saturation dome, meaning that shows the distinction between liquid, vapor, and the saturation region. So, for example, this peak of the dome is called the critical point of the liquid, and a line of constant pressure would look like this. And that saturation dome divides the liquid region from the vapor region for the saturation region. So the liquid region is on the left-hand side. That's on the left-hand side of the dome here. The vapor region is over the right-hand side of the dome. And of course, anything under the dome is the saturation region. And these lines of constant pressure you can draw at any given pressure, and they'll follow this general pattern. Well, they'll come up from the lower left, hit the saturation line, and then go flat across the saturation region, and then tip up again. And I'll make a little side comment here that that's for a pure substance. The lines of constant pressure will look like that. Some new refrigerants, the ones in the 400 family, for example, are not pure substances. They're not pure substances. They're blends. And one of the things that happens is that line is no longer flat. Introduces a concept called glide, which can make some systems more efficient. We're not going to get into that. That's kind of a subtlety here, even though the example we're using is a refrigerant that it does exhibit glide. It doesn't exhibit very much, so we're not going to worry about that for the purposes of this course, but you should be aware of that. Okay, so continue with our review of the TS diagram, temperature entropy. You should remember that cycles, thermodynamic cycles, can be represented as closed contours on one of these diagrams. And the area within a closed contour has the units of energy per unit mass. So the areas are amounts of heat or work per unit mass for closed cycles. So knowing where those corners are can tell us an awful lot about the amount of energy moving in our system. So the idealized, the thermodynamic ideal for a vapor compression cycle is, of course, like any of the cycles, it's the Carnot cycle. And so this is can be represented as a rectangle on our TS diagram. And the four corners represent four states of matter around the cycle. So we start at 1 in the saturation region and go through isentropic compression, going straight up to 2, which is sitting here on the corner here at the saturation point. And then from 2 to 3, we go through a condensation process. So we go from pure vapor to pure liquid, but we do it without changing the temperature. So it's isothermal condensation. And then from 3 to 4, we expand from a higher pressure to a lower pressure. isentropically, meaning that it has to be doing some work to do that, and goes back into the saturation region at the same pressure we started with, and then evaporates. It absorbs heat from the surroundings and evaporates back to cycle 1. So if we look at that, this is what it would look like from a kind of an engineering diagram, conceptual diagram. We have a compressor between 1 and 2. We have the condenser from 2 to 3. We have some device, some expansion, some sort of turbine that can allow the fluid to do work as it expands, and then goes through the evaporator. And of course, the evaporator is absorbing heat that boils the liquid, and at the condenser, we're releasing heat away. And so remember what we said about areas. So we have the area from 1AB41, this lower area I'm highlighting here. This represents the amount of heat that's being absorbed by the evaporator. That's what we're trying to accomplish in a vapor compression cycle. And the heat rejection is this bigger triangle, 2 to 3, and then down to A to B again. And the difference between those two is the net work, the work which is the compressor work minus the turbine work that's coming back. And we can talk about efficiency whenever we're talking about energy. This is a course in industrial energy efficiency. We should be careful and realize that when we're talking about heat pumps, and this is a Class C heat pump, that efficiency has a somewhat different meaning. And that's important to realize because these numbers are greater than 1, generally speaking. And so we try to get away from the idea of calling it an efficiency just to not have that confusion. We'll call it a coefficient of performance. Think of it as the ratio of the benefit to the costs. So the benefit, of course, is the heat absorbed by the evaporator, and the cost is the net work. And so we can go through the thermodynamics and say the heat's the temperature during the evaporation, the lower temperature, times the change in the entropy between those 2 points. And the work is given by that equation. And using our thermodynamics, our knowledge of thermodynamics, we can come up with this very compact expression for the idealized coefficient of performance for the Carnot cycle. It's the lower temperature divided by the difference between the higher and the lower temperature. And since the higher temperature is always bigger than the lower temperature, we can easily see that this can be a number that's greater than 1. In fact, it generally is. So that's one thing to keep in mind. In fact, for industrial systems, it's not unusual for a coefficient of performance to be in the order of 3 or 4. Okay, so here's some issues. We don't implement the Carnot cycle. We don't build a system that can work around the Carnot cycle. And here's the main reasons why. Okay, the compression process is in the saturation region. Let's go back to our original plot here. See, the compression from 1 to 2 is that entire line is within the saturation dome. And that means that compression is acting on a mixture of liquid and vapor. And that mixture of liquid and vapor it's very hard to design a compressor that'll tolerate that. Compressors like to work on just vapor. We have other devices that work on just liquid, and we call those pumps. But mixed phase is very, very difficult to design for. So we try to stay away from that. Another issue with the Carnot cycle is the isentropic expansion from 3 to 4 requires some device that does work and some place to put the work. And that's a little awkward. For one reason, there's not a lot of energy involved, right? And for another reason, it's just another device that has to be designed and built and maintained. And so it's not a lot of work to recover, and it costs a lot of engineering and manufacturing that we're not likely to do that either. And then the other part is that the temperatures of the condensers and evaporators will be somewhat different from the hot and cold environments in which they're operating. So, for example, if it's 90 degrees outside, that condenser is going to have to be operating at a temperature probably close to 100 degrees to be able to drive the heat from the condenser to the environment. Similarly, in the evaporator, it's got to get colder than the room you're trying to cool, or there'll be no way to drive the heat into the evaporator. So, we now have, we move away from the Carnot cycle, which is very theoretical, to something called the ideal vapor compression cycle, which is closer to the systems we actually use, and it gives us a framework to do the analysis. So It's much closer to the actual cycles. It still has its idealization, but that's fine. These are idealizations that fall within the realm of typical engineering analysis. The inlet to the compressor is saturated vapor. The compression is isentropic, so it's still a vertical line on our TS diagram. And we get rid of the expander altogether. Over between states 3 and 4, we put a valve, an orifice, right? And it just lets the vapor, lets the liquid from the condenser expand isenthalpically. So the enthalpy at the entrance is equal to the enthalpy at the exit. So this is what our system looks like now. We still have the compressor, we still have the condenser and evaporator, but now we have this valve, just this X here that just lets it expand. Generally no or very few moving parts. But it completely changes our TS diagram. Now we've got this contour in green here showing the compression going vertically from 1 to 2, but we're way up in the superheat region here. That tilting line is a line of constant pressure. It's an isobar, and that's now at 2. We enter the condenser as superheated vapor, and the condenser starts removing the heat, and it's driven off, and now we get down in the saturation region and slide over to 3 at the exit of the condenser, and that's now in pure vapor. From 3 to 4, we're expanding through our nozzle or our valve, our expansion device, and then we enter into the evaporator at a much lower temperature, and that's where the heat is absorbed. It goes from 4 to 1. The net area is much larger than the equivalent Carnot operating between those two temperatures, and so it's not as efficient, it's not as good, but it has that advantage of being able to build something that can actually make this happen. So we still have to account for the delta T. In other words, we have to make assumptions about what the temperature difference is between the temperature of the refrigerant in the condenser and the evaporator and the actual environmental temperatures. So the condenser has to be at a temperature higher than the outside ambient. Evaporator has to be lower than the space being cooled. We assume no pressure drop in the piping. And that's not a bad assumption if for no other reason the mass flow rate through these things is fairly small. They designed them to have, the HVAC designers talk about limiting the velocity of the flow, but it's the same idea, and basically they size the pipes so that the pressure drops are minimal. And we assume no heat transfer from the compressor. Again, that's probably not true. If you look at a compressor, it generally has cooling fins on it. We know there's some heat transfer. We can take that into account in our modeling by assuming or measuring or somehow knowing an isentropic efficiency, like 90 or 85%, which will take some of that into account. Okay, so our real cycle here would look more like this on our TS diagram. We move up into the evaporator allows some superheat, so from 1 to 2 we're actually riding up a little bit on this line. We're getting into some more superheat, and then this line from 1 to 2 is it's not vertical, it's pushing off to the right a little bit. That's taking into account the fact that there's some heat transfer going on at the compressor. Drives the 2 into further out into the superheat region. There's pressure drop along both in the evaporator and the condenser that is accounted for by the fact that we're now falling off of these isobars a little bit, and then the outside temperature and the load temperature are different from H and T, right? H and L. So those are all gives you an idea of the difference between an idealized and a real one. The ones that we will tend to not worry about much are the constant pressure. Like I said, those pressure drops are fairly small, so we're not going to really worry about those. We will have to worry about the delta T's between the loads and the low temperature, the outside temperature and the high temperature. And we'll also look at this superheat region out here, down here at the inlet of the compressor. Finally, at least for the purposes of this course, we're not going to worry about the efficiency of the compressor, so we'll still keep that line from the compressor, from that superheat point entering the compressor to the entrance of the condenser. We'll keep that as a vertical line. Okay, so the next step here is to actually do some analysis. Let's look at a real system, look at the specs of a system, and see how that fits in with our vapor compression cycle. So, but I'm going to stop this video here. We're going to do that in the next part of this module, and give you a chance to kind of absorb this and look at it. So, tune in to the next video.